Do you? Okay.
Okay.
Yeah, I think we're ready.
Great. Okay. Just give me 1 second. Okay. Let me share. Okay, so this lecture is about so-called optics. And it's one of my favorite topics in Haskell and one of my favorite lectures. So I hope you will enjoy it too. On the one hand, it's quite abstract and theoretical, but on the other hand, it also has very cool practical applications. So I hope it's a nice mix. And so the goal of the lecture is first talk about semigroup and monoid. We have done that already at the end of last lecture, but I'll quickly repeat that and then show some more examples. Then we'll talk about yet another monad, the identity monad. Then about an important type class called traversable, which is basically in this progression functor foldable traversable. And then, I mean, those 3 topics are like preliminaries, have nothing to do per se with optics. And then we'll talk about 2 types of optics, lenses and traversals. Okay, so let's get started. First, semigroup and monoid. So I think the beginning I can be brief because we did that at the end of last lecture already. So we have this semigroup class with this operator, whatever you pronounce it, I have no idea, given 2 elements of A producing a 3rd element of A. And as I said last time, you can think of, for example, addition or multiplication of numbers as examples. And there's only 1 law for this type class. I also mentioned last time it should be associative. So the order of how you parenthesize expressions shouldn't matter. Then we have monoids, which are semigroups with 1 additional method, mempty of type M, which is the neutral element. So the laws are that if you use this semigroup operation with mempty on the right or on the left, it shouldn't change anything. And the examples I mentioned before, addition and multiplication, of course, are also monoids because an obvious neutral element is 0 for addition and 1 for multiplication. And the default instance or the mother of all semigroups or mother of all monoids is list, where the operation is just given by concatenation. And in that case, the neutral element mempty is just the empty list, because if you concatenate with the empty list, no matter whether it's on the left or on the right, you don't change anything. I also showed you these examples. So there's this sum new type, which for numeric type gives you addition. So sum A with I don't know what to call it. If you I have no idea. Does anybody have an idea, Robert? Do you know how you pronounce this?
I sometimes call it diamond, but maybe join or merge, but diamond.
Right, diamond
yeah.
is nice. Yeah. Okay.
Yeah.
So sum A diamond sum B is just sum of A plus B. But for that to hold, of course, A must be a numeric type. And then it's also monoid. And as I said before, the neutral element is just given by 0. And similar, we have product, also gives a semigroup and a monoid instance for numeric types. And then the composition, I mean, the diamond operator is multiplication. And the neutral element is 1. So that's, I think, I've done all of that last time already. Now, one thing you could be misled to believe when you think of only those examples, addition and multiplication, is that it's also commutative, so that A diamond B is the same as B diamond A. Although already the example of lists and concatenation should show that that's not the case. So because it matters whether, I mean, if you compose Haskell and Kenya, you get Haskell Kenya. If you compose Kenya and Haskell, you get Kenya Haskell. So order does matter. So in general, monoids or semigroups are not commutative. And here's another example of a non-commutative semigroup or monoid. It's called first, and that's also defined in the standard libraries. So if we switch to code, if I go to this week's chapter and compile REPL, I think that's not in scope by default. No, I have to import, I think, data.monoid for that. And now it should be in scope, yes. So basically, as the name suggests, it takes the first element in some sense. So right, there's some confusion. There's also a version of first and semigroup, I think, which is different. But this is the one with maybe A's. And the idea is it takes the first just. I think I mentioned that before when we talked about parsing. There was this, when we talked about alternative and monad plus, I mentioned first before. So the rule is if you compose, or if you have one maybe, diamond another maybe, if the first one is a just, you just take that first one. And if the first one is nothing, you take the second one. We had this example, if you remember, with phone numbers, where there was like a cell phone number and a landline, and we want to get the cell phone number if it exists, but as a fallback, the landline. And there we used first. And this is indeed also a monoid, where the monoid neutral element, the mempty, is nothing. Because as you can easily see, if just A diamond nothing is just A, and nothing, and nothing diamond nothing is nothing, so that doesn't change anything on the left. And if you have it on the right, I mean, and if you have it on the left, then this rule immediately shows that nothing is a neutral element, or first nothing, I should say. Right. So here's an example. I mean, we can try it out. Let's see, mempty and first just X. First just Y gives me the X. So it gets you the first just in a string of maybes. And then, of course, we also have last, which is the opposite. So it gives you the last just. So anything diamond last just is this just, and X diamond nothing is X. And then again, last nothing is the neutral element. So if we try the same thing here with last, then we get the Y, the last just. Okay, and then there's a somewhat different example. It's called endo, just not sure whether that is in scope. Yes, it is indeed. So endo, for the mathematicians amongst you, there is a term in mathematics called endomorphism. That's a map from some space or set to itself. So we see it's just a new type wrapper around functions from A to A. So not arbitrary functions, but functions where the codomain and the domain are the same. And that is a semigroup by function composition. So you can diamond an endo F with the endo G by just composing F with G. Because, I mean, with composition, that's only defined if the target of the domain of the first function is the codomain of the second. But because we have endomorphisms here, where it's always the same, this trivially works. So it's always well defined. Was there a question? No.
No.
Okay. So that's an endomorphism. So endomorphisms are a semigroup. And of course, we have a monoid instance as well, because the identity function is the neutral element. If you compose with the identity function on the left or on the right, it doesn't change anything. There's some ruckus on the, so maybe somebody has to mute himself.
Harit, could you mute yourself, please? Harit. Thank you so much. I
Okay,
think
so
we had a question at some point that disappeared.
oh, okay.
Samson, did you have a question? No? Okay.
Sorry, no.
Oh, yeah. No problem.
Okay. Okay. So I can do this example here. So what was it? I mean, it doesn't matter, of course, times 2. I should say where I am. Let's say int. So this is just function composition. So I have the 5. I apply times 2 to it. It's 10, and then successor 11. Right. So that's yet another example of semigroup and monoid. So they are really everywhere. And I think until now we've only seen examples where it was monoid. So, but there are examples where it's just semigroup, not monoid. So for example, we saw this non-empty class earlier. If you remember, for non-empty lists, so the idea was that the constructor takes an element, the head, and then an ordinary list, which can or cannot be empty. But this guarantees that it's never an empty list, because we always have this explicit head. And if we see it should be a semigroup instance. So for example, I can do whatever x so it's just concatenation. So we get, I mean, by composing or concatenating these two non-empty lists, we get again a non-empty list where the first element is x, and then the other elements are y, z, capital A, B, C. But of course, if you think about it, this can't be a monoid, because the only list you can concatenate on the left or on the right that doesn't change anything is the empty list, but the empty list obviously is not non-empty. So in the type of non-empty, there is no neutral element for concatenation. So this would be an example of a semigroup that's not a monoid. But most of the time, I mean, most examples, I mean, monoids are very common. So very often we indeed have a monoid instance. Right. So are there any questions to semigroups and monoids?
Not so far.
Right. And actually, I mean, when we talked about parsers, we had this alternative and monad plus classes. And in principle, they also imply that parser A for fixed point, for fixed type A is also a monoid. I mean, that's basically what alternative says. Alternative basically says for every type, it's a monoid. And same for monad plus. So we have basically seen examples already as well. And I mean, in mathematics, lots of things are monoids, but also, I mean, computer science, like lists, for example, you saw now. So lots of data structures are monoids. So yeah, it's a very common and very useful type class. Okay, so let's next talk about the identity monad. Let me just check whether that's in. Let me just close because by importing this non-empty, I polluted my namespace. I think identity is not in scope, so that's in data.functor.identity in the base libraries, but I can define it. So identity is just a new type wrapper, basically. Is it get identity, run identity? Typo, sorry. It's just a new type wrapper. Identity A is just a new type wrapper around A. And actually, we can turn it into a monad. So we can do instance functor identity, it's the usual. So fmap is lift m. Do this, then I need instance 6, and I must import something from control monad. Right. So applicative. U is just given by the identity constructor. And as always, our app is just app, which I also need to import. And finally, monad. So as always, return is just pure. And bind identity A to identity B, identity B. If I have identity A and some continuation. So this, we have an A now, and we can apply this K to it to get an identity B. So it's just function application. Right. And I told you before that one way to look at monads, or one way I like, is that monads give you the potential for certain side effects. So IO gives you real world side effects. State gives you like mutable state. What else did we have? Maybe gives you like exceptions. Either gives you, or either string gives you exceptions with error messages. List gives you non-determinism. And identity is the monad that gives doesn't give you anything. So it's basically the monad that gives you no side effects. So it's just wrapping pure functions. So as an example, I mean, that means using the identity monad, we can write pure functions with do notation if we want to do this. So for example, we could do add 3, I mean, in a contrived way. Or let's say not add 5, whatever. Let me just look at this example, what I have there. Okay, fine, 50 int. So run identity, do x identity 42, let y equals 8, pure x plus y. If we reload, it was just my editor acting up. If we reload, then 50 is indeed 50. So, I mean, of course, nobody would write it like this, just to show you that, I mean, it's a monad, so you can use do notation, but there's nothing special you can do. You can't do anything else that you can't do with pure functions. So normally you wouldn't do that. And of course, I mean, you would ask yourself, why can that be useful? A monad that doesn't do anything. But I mean, the same question you can ask and probably have asked yourself about the identity function. And I think we have seen several occasions already where the identity function is useful. And we will see later today why the identity monad is useful. So often it's useful to have, like as a base case or ground case, something that doesn't do anything. So actually the identity monad is very useful, but it doesn't do anything. Are there any questions to that?
There's none written, but if anyone has questions and wants to actually like say them, feel free to do it while Lars is explaining.
Yes, I'm not sure whether people can unmute themselves automatically, but I mean, in the past I couldn't, but yeah, you can also just raise your hand or something, and then Robertino can let me know that somebody has a question.
I've allowed them to unmute themselves.
Okay, perfect.
Okay, thank you. Right, so now, I mean, the first one, semigroup monoid, was just a repetition of last time, and identity is not very interesting at the moment. Now we come to something that I think is very cool, a very useful type class, and also one that appears quite frequently. Almost all 10 container types like trees and lists and so on are instances of this. So, and it's almost magic. I think it's very cool. So if we look back at map M, let me just see. Okay, that's unfortunately already in scope. So let me just hide that. So just as a reminder, I think we have first seen that when we talked about I/O and then later other monads. So if you have a monad and a function from A to, I mean, an effectual function from A to B, then if we have a list of A's, is that what I use here? Yes, into M of list of B's. And the definition, we have seen it several times. So if we have the empty list, I mean, there's not much we can do because we have no A, and this function here is only useful if we have an A. So if we have the empty list, there's nothing. So the only thing we can possibly do is pure empty list. And if we do have something, an element, then we can apply to the first element. And so that's then of type MB. So we can bind against this. And we can recursively map M F over the tail of the list. And now we have B and BS. So now we can do pure B, BS. So that's, I think we have seen this definition several times now. And it's very useful. I mean, you can, I mean, it's like map, but it allows effects. And then, of course, once you have this effect, it basically pollutes the result. So you get not a list of B's, but a list of B's in monad M. So one example is if we, for example, use the IO monad and do put string line, map M, put string line, and now we have a list of strings. Haskell is great. It will, I mean, apply this function put string line to all the elements, and we do see the effects. It prints them on the screen, but the result of put string line is units. So in the end, we get a list with 3 units out. And there was also a version of map M underscore, which forgets the results. So in cases like that, because it's not very interesting to get this list of 3. units. Okay, and so yeah, this example. But now if we look at it, and I mean, we have seen a couple of some examples of applicative and applicative style yet. And just as a reminder, often applicative is strong enough. You don't need monad if you know in advance which effectful computations you want to do. So you only need monad if what you intend to do depends on the result of a previous effectful computation. In this case, it doesn't. I mean, we just apply this F to all elements of the list, and we don't care about the results. I mean, we do care in the end. The end result depends on the results, but what we do, the effects we perform, doesn't depend on it. And that means that actually we don't need the monad constraint here. Let me just check whether, okay, no, it's not. So we can actually drop this monad constraint. Let's call it map A for applicative. And then traditionally an applicative functor is denoted by F, not by M, but it doesn't matter, of course, it's just a renaming. And now, of course, we don't have do notation, although I could say that there is an extension in GHC called applicative do, but never mind that. But we don't need do notation because we can just use applicative syntax here. This is exactly the same thing written applicatively. And this basically emphasizes what I said earlier, that we don't need the power of monad here. So we also have this for applicative. So that's the first observation. Let me check on the right. I mean, we could do the same thing again. The same example that I had before with map A. Of course, IO is a monad, but it's in particular applicative. So that still works and has the same result as before. Right. And now, I mean, the plan for the next couple of slides is now to realize that map A is insanely powerful. That basically once we have map A, we can rediscover all sorts of useful things. For example, we can rediscover map. So the trick is, and now for the next couple of minutes, and actually in a more general sense for this lecture and the next, to pick appropriate things like applicatives in this case. So we want to basically rediscover map or define map in terms of map A. And so the question is, what A do we choose? What applicative do we choose? And I hope it's relatively obvious after what we've done before. I mean, map deals with pure functions, so there are no effects. So we should pick an applicative that's made for no effects. And of course, very cleverly, I introduced the identity monad before. So the idea is to use the identity monad. So let me hide map as well. We can just use map. So as before, I mean, our plain old boring map. F access. So the idea is to just use map A with the identity monad. Now, of course, the identity monad expects if we substitute identity for F here, we need something of type A to identity B. But we have something of type A to B. But that's no problem. We just compose with the identity constructor. And apply this to the list. And now we have a problem, I mean, a small problem apart from that, because I mean, now we get identity list of B, but we want a list of B. But identity, we can just unwrap with run identity. And that would work. And of course, we can, if we want to write that more compact by eta reducing like so. So basically the trick is to just wrap F into identity. Then we are in an applicative. We basically have an effectful function, even though it doesn't have any effects. Use map A and then unwrap the identity new type constructor again. So we can try this out. So map whatever. I mean, my standard example was always to upper. So let's do this again. So map to upper Haskell as before gives us Haskell. So, I mean, this just shows that this map A is so powerful that it basically removes the need for map. Because by just picking the identity monad, we will recover map. Right. So last time I told you also about fold map. So just as a reminder, if we ask for the type of fold map, so if you have some foldable container and a monoid M and a map from A to M and a container of type A, we can convert it to M. And the idea is, so if we have fold map, for example, for lists, so we have F and a list of what, or let's say, yeah, it doesn't matter. A list of something. Then the idea is that we just apply this function F to each of the elements. And then because of this monoid constraint, these are now of type M, which is a monoid, so we can compose them with this diamond operator. So that's what fold M does, fold map, sorry. And the cool thing is that similar as how we turned recovered map from map A, we can even recover fold map from map A. But if we want to do this, so let me now hide fold map as well. But before I do that, maybe we should have an example. So for example, show. So fold map show. 1, 2, 3, 4, 5. So the monoid in this case is list of characters, strings. So show takes an int and converts it to a string, and string is monoid, where the monoid, the diamond operation is concatenation. So this applies show to all the elements of the list. So we get the string 1, 2, 3, 4, 5. And then it uses the monoid operation concatenation to concatenate all those strings to this string. So maybe it would have been wise to also have something that has more than one digit. So, right. So I just wanted this example. If we now try to re-implement this, that this same example still works. Let me hide this. So now it shouldn't work. Okay. Right. So now we want to implement fold map. Let's say just for lists. I mean, it was more general. It was for arbitrary foldables. But let's just do it for lists. So we have a monoid M. We have something from A to M. Now a list of A's to M. And I want to use similar as I did for map. I want to use this map A. Right. So now if we compare signatures, map A, the function must be from A to applicative, whatever applicative we want, B. But if we compare this with here, we have an M, independent of A, always this fixed M. So that looks a bit weird, and it looks as if it's not possible what we want to do. Because, I mean, it should somehow depend on B, but we want fixed M. However, a second. Right, so const is non-corp. Maybe remember that, no, I think we haven't had that. So the idea is we need some type constructor that always gives us an M, no matter what B we put there. Well, we can just define that. So we can say new type, we can call it const. Let's call it MB. And we just say it's const M. Right, so we have something here of the right shape. So const M is of kind star to star. So we can use it for F. And it basically just wraps an M, so which is very close to this. I mean, it's not exactly this. It has this const constructor in front of it, but I mean, that's just a new type wrapper that we could also get rid of here when we did map. So with wrapping and unwrapping accordingly. So that's nice. So our idea is to basically write this. So we use this, I mean, we use our F and compose it with const. And then as before, we apply to XS, and then it wouldn't type check because then we have a const M and not an M. So we need get const again, like this, and then I can eta reduce again, like so. Okay, but now of course we get a problem that we don't know that this is an applicative. I mean, this map A only works for applicative, and const is, first of all, I mean, right now is not even functor. But functor instance is easy. So instance functor const M, where, so what do we need? Fmap, we have something from A to B, get something from const MA to const MB, fmap F, const M. But this is simple. I mean, because this const MB, we again just need an M. There's no A or B anywhere inside. So we can just say const M and the function doesn't matter. So we completely ignore the function and just keep our M as is. Although note these are different types. So this is a const A, this is a const MA, this is a const MB, but they look the same. So that's good, but we need applicative. So if we now try instance applicative, const M, so we start getting problems. So now we need pure from A to const MA. So pure A equals, so const, and now we need something of type M here. But where must that come from? I mean, we don't know anything about A or M, so it's impossible to write this instance, even the pure, because there's no way for us to conjure up an M out of thin air. And it gets even worse for this, because we need const M A to B, const M A, const MB. So we have some const F, which is of type M, and some const A, which is also of type M. And we need the third thing, which is of type M. So we have two M's, F and A, and need an M. So we see this is, I mean, this is impossible. If we don't know anything about M, we can't come up with M's. However, what do we need? We need some fixed element of M, and we need to be able to combine two M's to a third M. And if you have paid attention, like at the beginning of the lecture, then that should scream monoid and semigroup. So if we demand that M is actually a monoid, then we do, what's the problem here? Sorry, 3Ps. If we actually have a monoid, then we do have an element of M that we can pick out of thin air, namely mempty. We don't need this. And we have a way to combine two M's to a third M. namely the semigroup diamond. So const in general is not applicative, but const if M is a monoid is. And now this compiles the fold map, because now we have our applicative. And if you think what it does, I mean, it does exactly the right thing. So we can try this out. If I now try my earlier example, I get the same result as before. Right, so we have this map A, which works for arbitrary applicatives. And we saw that for clever choices of the applicative, we could rediscover both our old map by using identity for the applicative and fold map by using const for the applicative. So this is like cool. And it's basically a prelude or like a practice or training for what is to come with optics. Because of course, optics is all about picking appropriate applicatives or functors for stuff. And this also should put identity and const on your radar. So even though they both look quite boring, I mean, const completely ignores this B type and just has M's, and identity doesn't do anything. It's just a new type that doesn't do anything. These examples hopefully show that such simple things can be useful, because you can then apply them like for something as general as this map A, to basically recover old things. So we see that this map A is a really powerful function, because it basically gives us back map and fold map. Okay, I did this, I did that, did this, did all of that. Right. And now so this one drawback is this only works for lists, right? And I mean, we glimpsed before that actually it works. I mean, this map M actually works for foldables, but basically just lists. So and I mean, it's nice, but as I said last time, I mean, lists, even though they are all over the place, are often not very efficient and so on. So let's see whether we can do even better. So for that, let's look at our tree type again, tree A. So we have, what was it, leaf A or node tree A, tree A. And let's do an example tree again. Something simple, node. Okay. Right. And now inspired by this, which worked for lists, let's see whether we can do something similar for trees. So let's call it map T for map trees. So for applicative Fs and a function from A to FB and a tree of A's, can we get F of a tree of B's? So I have just replaced list here with the tree functor here. Okay, let's see whether we can do this. So there are two cases, leaves and nodes. So if we have a leaf, what can we do? I mean, we have our function f, and we have an element a of type A. So we can apply f to A, and then we get an FB. So we can do this, but that wouldn't be type correct. I mean, we have an FB now, but we want an F of tree B. but we know tree is a functor, although I haven't said that yet. So let me derive this. So we have an FB, we want an F tree of B. We don't know anything about F except, oh no, sorry. I don't need that tree as a functor. I mean, it is, but I don't need this. Sorry. I was confused. Right. So we have an FA, sorry, an FB. FA is of type FB, but we want an F tree of B. So we don't know anything about F, but we know it's applicative. So in particular, functor. So in particular, we have fmap, which means given a function from B to tree B, we also get something from FB to F tree B. And we do have a function from B to tree B, namely leaf. So we can fmap leaf over this and fmap, sorry. And now it complains just that it's right. Or of course, we can write this nicer like so. So that's basically the only thing we can do in this situation. That's again an example of what I said like a couple of weeks ago, why polymorphism often helps you implement stuff, because I mean, here we don't know anything about F, A, and B. And that means we only have very few things we actually can do, which makes it easier to actually do them. Okay, and then we have the node case. So what can we do here? Well, we can recursively apply map T to the left child and to the right child. But now we have like an F tree B and another F tree B, but how do we compose them to one F tree B? And obviously, I mean, inspired by the first case, we want to use the node function. And now we need to use that F is actually applicative. And then we can do node. Right. So that compiles. So we have that now. So what we did earlier, I had this example where I had map A put stringline Haskell is great. So now let's try map T put stringline for our example tree. And it works. So it goes over these leaves, puts stringlines them, Haskell is beautiful, and replaces each leaf with the result of put stringline, which is just unit. So we have a tree of the same structure as before, except now the leaf values have changed to the result of put stringline. And the effect has been transformed while I was traversing these leaves. Okay, so now the next stuff should be obvious. So we saw that we could recover map from map A. So once we had map A for lists, we could get map for lists. And remember, map for lists is just fmap. So now the idea is that we can do exactly the same here. So we can get a functor instance for tree. I mean, we could derive it, but so what did I do here to get map? Let me just copy this. So this was how I got map. And the only thing now I have to change is I replace this map A with T. And the same trick with identity works as well. So I had my example with this map map to upper earlier somewhere here. So now I can do fmap to upper on our example tree. No, I can't because it's a tree of strings, so to upper doesn't work, but I can do map to upper, for example. Right. And we recovered our old, well-known acquaintance, the fmap, the functor instance for our binary trees. Finally, fold map. I got this here. So can we do the same for trees? Let's call it fold map T maybe. So just instead of lists for trees. And indeed, the same definition works when I replace this map A with map T. So now fold map should also work. Now I just need an example. For example, identity. I can do fold map T identity on tree. And the identity, so the leaves are strings. So it applies the identity. So it's again, Haskell is beautiful, but now considered as a string monoid. So the monoid operation will smash them together. So we get this. So now you hopefully see a pattern. So we have lists and we have trees. For lists, we have this map A. For any applicative f and a function from A to FB, given a list of A's, we get f of a list of B's. Now for trees, we have this map T, applicative f, function from A to FB. Giving a tree, we can get an f of a tree. And once we have this, we can get the f map, the functor instance, for free by plugging in the identity monad. Same here. And we can get the foldable instance for free, because I told you last time that in the foldable class, it's enough to implement fold map actually. So we get the foldable instance for lists from this map A. And we get the, so I should have actually, sorry, that was maybe not a good idea to call it fold map. So I should just have set foldable tree and then just called it fold map. And now it's complaining for some reason. Because I need to import data.foldable, I think. And now it probably will complain about my, what doesn't actually. See. All right. Okay. And now hopefully you see a pattern. So something of this shape. I mean, this is possible both for lists and for trees. And once we have that, it gives us functor and foldable for free. So it seems to be, once we have a function of this shape, we have like more, I mean, we have something that's more powerful that implies functor and foldable. And enters the traversable class. Let me hide this as well. Did all of this. So we have class T is functor and foldable. Then a new class that's called traversable. And it only has one method, traverse, which is exactly what you hopefully now expect. So for an applicative f and for something from f to A to FB, and some container of shape T, we get f of TB. So we saw that both lists and tree can be made an instance of this class. So we have instance traversable list, where traverse is our map A. And we have instance traversable tree, where traverse is our map T. And furthermore, we have something like, what is it called? Just a second. So we have fmap default, it's called. No, I don't want to import it. No. So if we have a traversable, we have A to B, then we get what we expect of fmap. And this is just what we did here. Twice now for trees and for lists. So once we have this traversable, we can just use it to get a functor instance. And we have a fold map default, traversable T A to M. Monoid M, A, M. And there I can just copy what we did here. What is wrong now?
It's a typo in the signature name. Fold map. The M is lowercase.
Oh yeah. Is it? It should be this. Oh yeah, and it's not traverse. Right. So that means this traversable class is a bit, I mean, similar. I mean, functor, foldable, traversable is a bit like functor, applicative monad. So where monad is the most powerful one, and once you have return and bind, you can get fmap and pure and app for free. It's somewhat similar to traversable. Once you have traverse, you get fmap and fold map for free. So if you have something traversable, you have like default implementations for functor and foldable by using this fmap default and fold map default. And then you can traverse things. Let me see. Right. So we saw all of this. And intuitively, I mean, I always said foldable is, I mean, you can think of foldable as containers. The same is true for traversable. I mean, that implies foldable. But somehow traversable is like you sort of can keep the structure or inspect the structure. With container, you have no way to know how the A's are arranged in a container. You just know there are A's in there and you can get them out in form of a list. But by converting basically the content of a container to a list, you lose all structure that the A's might have had in the container. Whereas traversable somehow remembers that structure. I mean, that's a bit vague, I know, but it takes some time to get intuition for it. And a cool thing is, I mean, this is a bit mind-bending maybe, but if I ask for traverse composed with traverse, it actually composes. So if we have one applicative and two traversables, T1 and T2, and an effectful function, then it takes like a container of containers to F of the same container of containers. So this is nice because this, if you look at this class here, then the cool thing is that basically this is again of the same shape as that with one T added. So it nicely composes. I mean, maybe you should think of that yourself. So somehow the shape of this traverse, the signature, especially if you basically add functions, parentheses here, then you can see that you can compose one traverse with another traverse, and you get again something of the same shape. So that means we can not only traverse one container, but nested containers. So for example, if you have a tree of lists, which we have, I mean, we have a tree of strings, and strings are lists of characters. So we have actually two, I mean, this tree here, this example tree, is actually of this shape because it's one traversable is tree and the other traversable is list. So we can actually apply this here and do traverse dot traverse. Let's say print of our example tree. And now it traverses all the leaves of the tree, and then in each leaf, all the characters in the string, and applies print to it. So it prints all the characters on the console. Right. So that's actually, I mean, it's a very cool class. And the really good news is also it's derivable. So there's, I mean, we already saw there are these GHG extensions, derive functor and derive foldable, and there's also derive traversable. So we basically wouldn't have had to write a single line of code to get this. We could just derive traversable, and then we get the traverse for trees, this map T, automatically. GHG can derive that automatically. Maybe as a last example of, let me just 1 second. Let me do 2 things. First of all, I want to rename this here to traversable. Because I now hit so much that I don't want to hide later. And let me also import MTL. Let me just give me a second. Let me, whatever, save it. And open this new one and rename this. Let me delete everything here. Load again for good measure. So one last thing, if I import control monad state and maybe run state. The state monad, just a last example for traverse with different applicatives. So we have seen examples now for identity and cons. That was the trick to get fmap and fold map. We have seen IO, my example here, to print to the console. Let me also do the state monad. So we can do something like label tree. Remember when we talked about monads, I used tree labeling as an example. So the idea to take a tree of A's and turn it into a tree of int, A's, where the labels are, all the leaves are labeled from left to right with a number starting at 1. So we can do this now with, so tree of A to very elegantly with traverse. If we use the state monad. So I basically want to use run state, or actually I want to use eval state because I'm not interested in this state. So eval state. So I need the stateful computation and an initial state. We come to this in a second. The initial state is 1. And here I use traverse, and now some suitable function from A to state int, A on my tree. So this, yeah, okay, fine. Right. So now I'm using traverse where F is the applicative, F is the state monad. So F goes from A to state int, A. Okay, and what do I do? Well, I want to label the tree. So I get my current state. I put the next label as the new state, and I use the old label to label my tree. Right, and now hopefully I can use label tree on my example tree, and tada, it does label it correctly. If you remember, when we did that with monads, it was already quite neat. I mean, quite a neat solution, but it wasn't as neat as this. This is basically just a case for leaves that we had back then. But we explicitly had to do it for nodes still. But this traverse now basically takes care of that. So it automatically traverses the tree and does the right thing. So at each leaf, it looks up the current state, increments it by 1, and labels the leaf with the current state. So that's, I think, is the most elegant solution to this tree labeling problem using purely functional programming without like mutable state in IO. Right, so I think this completes that. And now we are ready for optics, but I think we should have a break, but maybe somebody has a question before.
We can wait for a bit, or else we can take a break if someone wants to write down the question. Oh, we have one. Why
Okay.
does traverse map to upper tree results to a list? And traverse map to upper tree.
I think, oh yeah, I mean,
no,
traverse.
Yep.
Yeah, sorry.
Results in a tree, as it should.
Okay, let's see. So we have, good question. Interesting. I actually wanted to use that example. So what's the type of this? Sorry, traverse. So the question is, where do we use traverse? So what's this map to upper? Map to upper. I mean, the question is, what's our applicative F? So let's first look at the function here. So we have map to upper. So map to upper. It takes a string and returns a string, which is a list of characters. So this here is our A string, and this here is our FB, right? Because traverse takes an A and goes to FB. So that shows us F is list, the list applicative, and B is character. And because traverse, so that means that the type of traverse map to upper tree, we know it's an F of tree B. So it must be a list of tree character. So that's why we get a list of tree characters. And now we must just see, okay, so the applicative is non-determinism, right? So that means it will, what it will do in this specific example. So it goes to the first leaf of the tree, and then turns them all to uppercase, but picks non-deterministically one of those letters, and the uppercase version of it. Same for the next leaf, same for the next leaf. So it will start with H, capital H, capital I, capital B. Then H, capital I, capital E, H, capital I, capital A, and so on, H, capital I, capital L, then capital A, and so on. So we should get whatever, what's it said, 7 times 2 times whatever, how long beautiful is, like quite a lot of like possibilities. I think that's, yeah. So that explains that. Yeah, that was a very good question. I actually had thought earlier I wanted to use list monad as an example, but I forgot about it. So thank you for the question. So yeah, you can get surprising results when you do these things. Are there any other questions?
Not so far, but what I was saying before is that if we take a break now and someone wants to ask
Sure.
questions during the break, we can answer it when we get back.
Of course. Should we continue at past?
Yeah.
And then if somebody has a question, of course, we can ask it.
Okay.
Okay. Talk to you at past. Thank you. Okay, I'm back. Should we continue? Or are there any questions?
No new questions.
Okay, then let's go to optics.
Your favorite.
My favorite. Right. And first, let's talk about lenses. Because I mean, it's called optics because it allows you to zoom into data structures, do things, and zoom out again. And there's a whole zoo of optics, and we will talk about 2 or 3 or 4 in this lecture and the next. But the like maybe most important one, or at least like the first one, is called lenses or a lens. And as a motivating example, let's look at this. And so it has nothing to do with optics or anything. It's just a motivating example why you would want something like this. So let me just copy this. I haven't done that yet. So we have a company type. This actually should be a new type. And so company has staff, which is just a list of persons, because we haven't defined persons yet. So, and the person, let's say, has a name and an address. Of type address. Let's say address is just a new type around the name of the city. Obviously, this is like a silly type. I mean, in real life, it would of course be much more, would have many more fields. Okay. And in case you wonder about the underscores, they don't mean anything. I mean, it's not like with, I mean, we know for patterns, if you use an underscore, it means you don't use the variable on the right-hand side. If it's used as the name of a record field, it has no meaning. It's just convention in the context of optics for record types to have this underscore. And we will see why like later in the lecture. But it's just, it doesn't mean anything. So the underscore is not important. So that has nothing to do with anything. Right, and we can have an example person or two. So Karina is a person. Her name is Karina. And her address is address. Myself. Sorry, ignore me. Okay. Then we can have IOG. It's a company. IOG is company whose staff is myself and Karina. Okay, so far so good. I mean, nothing. I mean, I think we have seen that in the first lecture or the second. So I mean, record types, very basic Haskell, nothing to it. But now I have a little task for you to write. I mean, we can just load this module now. We have this IOG company, right? And now I want you to write as a little exercise. Let me just check the, okay, string company. Function like this. Move all staff of a company to the given city. So new city or city. Okay, so we have a company. You have a string that's the name of a city, and the idea is that in the end you get another company with basically the same staff, but for each staff the name is untouched, but the address, the city in the address record has been changed to this new argument. Okay, and maybe in 10 minutes you can try to implement this, and it's not a trick question. I mean, it's just basic, very basic Haskell.
And
so maybe, yeah,
if you
sorry.
want, you can send it in a direct message to us, or
Yeah,
just
sure.
to avoid
Or,
spoiling to the other to everyone else.
yeah, sure, you can do that. So I don't know, until in 10 minutes, let's say 48 or something.
Yep. Okay.
Okay. Right. I mute myself again, but then somebody has to unmute me again. I can't this time for some reason. Anyway. Okay, should we continue?
Yes, I didn't got anything, so maybe if someone is halfway through, you can just send it, or maybe just, okay, we have one. Jason already
Okay,
proposed the solution.
does it look right to you?
Yeah, it looks interesting though. I can send
I
it after.
Right, I just want to make it a bit more difficult for myself, because with these new types, I mean, I did that to get it on one slide, but it actually gets more interesting or difficult if you have more than one field in company and in address.
Right.
So just let me just whatever. Let me just make it a bit more interesting by
Yeah.
uh,
Yeah, the solution looks nice. The one we got.
okay, cool. But it's hopefully like somewhat complicated.
Yes.
Right. Okay, so now of course I need to right. Okay, so I mean, how would I want to do? So I just added fields here because then it gets even more complicated. And maybe it makes the problem clearer. So what can I do? So I mean, I want to update like something deep inside this nested record. So in the staff record of the company, for each person, in the address record of the person, I want to reach into this city field. Right. So I can use record update syntax for that. So I keep the existing company and I just update the staff field. But with what do I update it? Well, I mean, staff is a list, so I can map an update function over each person of the original staff. So map f staff. Of course, I need to define this f. So this goes now from person to person. So f of a person is the original person. When now I update the address to like G applied to the original address. And G is now from address to address. G of an address is the original address where I update the city to the new city. So this would be one solution. The same, literally the same code would also work for you. And maybe you can take some shortcuts somewhere. Maybe you don't need all these helper functions. Let's try whether it works. So go to Nairobi IOG. Right, and now, I mean, of course, the country is wrong now, but never mind that. So it's Nairobi. So that works. But the point is it's somewhat tedious, right? And also frustratingly, I mean, if you think of like JavaScript or something, you could do something like, I don't know, for each person, I don't know. I mean, this is now some pseudo language, but or Python or whatever, you could do person dot address dot city. I mean, something like that, right? So in like imperative languages where you can change stuff in place and where you have like record with this dot syntax that we are used to from object-oriented programming, you can do something like this. And in particular, you can do this dot stuff. So person.address.city. So you can reach deep inside like a nested record or nested object. Whether that's good practice is a different story, but I mean, you can. So it would be very compact and very clear. Whereas here, I mean, it's quite complicated. Right. And basically, optics is about making it just as nice or even nicer than in imperative languages. So I mean, this is an example solution for the original types. So to do it quite compactly. Sorry. So I mean, the point or the takeaway is that, I mean, these record accessors that we have in Haskell are fine for flat records where you just have a record and where the types of the fields are like primitive types or non-records. But it really becomes a pain to work with it if you have like deeply nested records, like in this example. And if it was an imperative language, I mean, we had to have this dot, and then it's easy to update something in place. But in Haskell, we don't update structures in place. So we prefer immutable data structures. And the good news is that we are, of course, not doomed because it's Haskell after all. So when we introduced monads, we talked about the programmable semicolon. So now we'll create a programmable dot. So that's basically optics, programmable dots. And so as a teaser at the end of this lecture, hopefully if maybe we run out of time today, but then, I mean, once we get done with lenses and traversables, then we can go to like this. So we can say set staff.each.address.city CS. So that's even nicer maybe than my pseudo Python solution. Right, so that's the goal, to be able to write this. And if we look at underscore staff, for example, which just has, I mean, we can look at it. It's just a function from company to list of person. And they are, I mean, as functions, of course, composable, and composable is always good because in functional programming, we like to compose problems into smaller problems or compose solutions out of solutions for smaller problems, out of smaller building blocks. So for access is actually good. I mean, for example, I could do something like city composed with address of Lars. And why is this? This is not good. Did I oh yeah, because sorry, country and this are the wrong, sorry. Which is a good point. I mean, I wanted to be lazy and just use this syntax to construct it, but I of course made the mistake now that I mixed up country and city, which is a good like didactic thing to why one should never do this. So normally I always use the more like elaborate but clearer version where you don't have to remember which is which. So this is what I should have done. And now hopefully. So this is nice, right? That I can compose these record accessors to reach deeper into a data structure. So I can reach 2 levels deep into the address, and I mean from the person first into the address and then into the city by just composing. So that's nice. So if it was just about lookup, then Haskell is already beautiful for this. I mean, it's the wrong way around. In the imperative language, it would be address.city, not city.address, but nevertheless, it's nice. But the problem with this task is that we didn't just want to look, we wanted to update something. And we do have record update syntax, this thing, but that doesn't compose very nicely. That's why I had to do this awkward solution with these two helper functions. So the goal is to change this so that we have composability not just for lookup, but also for, I mean, not just for getters, but also for setters. Right. And so the idea is to make these accessors first-class citizens. And we define our lens type. I mean, this will change over time, but this is our first try. So lens is supposed to be a first-class accessor. So let's define data lens SA. And those type names are traditional. So I have no idea why it's called S, but it is in literature. So it's the lens. Let me just check. Okay. And it's called lens because it allows you, as I said before, to zoom into a data structure. So a lens has two parts, a getter. And the idea is S is like the big thing, the record, and A is the small thing, the field. So the getter will, given the whole record, give us the small field. And the setter, you just get right. So given a new, given the record and a new value for the fields will update the record. I hate this. Right. Okay, so that's a lens, or at least our first version of a lens. And before we go on, let's just implement it for our things. And the name of lenses now, in this case of records, traditionally has the same name as the field, but without the underscore. So staff will be a lens from a company to a list of persons. So staff is a lens. And let me just see whether okay, I was lazy again. So first the getter. The getter is just our record accessor. And the setter, so given a company and a new person, and a new list of persons, we keep the old company and set, underscore staff to this given list using record update syntax. Okay. Now we can do the same thing for address. So that's a lens from company, from person to address. So address lens. So the accessor is address, and given a person and a new address, we use record update syntax to change the address field in the person to the new address. So now city. Do I have others there? Oh, name. Okay, fine. So name, lens from person to string. Name. Name. Address, city. And now, of course, I also, now I added these fields, so I also have domain, lens from company to string. The accessor is domain, new domain. Okay, now finally city is from address, is a lens from address to a string. So city is the getter, and given an address and a new city, I update the address by setting city to C. And finally, now I also introduce this country still. Right. And you see here already that it's like easy but tedious to do this. I mean, if you have like big records with lots of fields, then I mean it's brainless, because once you have understood it for one record, I mean it's just boilerplate. It's always exactly the same code, but it's tedious to write it by hand. And if you use one of the standard optics libraries on Haskell, then you don't have to write that by hand. So there's a mechanism called template Haskell that does that automatically for you. So you don't have to write these things by hand. Right. So as I said, so there are ways to do this automatically. It's easy, but mechanical and boring. And now we can do things. So for example, we can say get after we reload. Why? 45. Okay, fine. I think person I didn't use, but for good measure, I can. Okay, that's just name clashes. Anyway, right, so let's try again. Good. So now I can use it. I mean, for example, get class name. Class name. I do other way around. Get name. I mean, the lens is, first comes the lens, right? Or whatever. Get city. Get address. Carina. Right. And I can also try the setter. So if I have set domain IOG crypto, then I change the domain from blockchain to crypto. Okay, so that so far so good. But of course, at the moment, it's not really better than record syntax before. I mean, the getter definitely is just longer. I mean, before I had the underscore name, then I wouldn't have needed this get. And set is maybe debatable, but nevertheless, I mean, it's not much more convenient than record syntax. But before we show why it's actually cool to do it like this, first a remark that even though the motivating example here was for records and fields, we are not restricted to that. I mean, nowhere it says that it must be a record type. So for example, we can also write lenses that are traditionally called _1 and _2. We can write a lens from a pair of A and B's to A. So it reaches into a pair and focuses on the first component. So how would we do that? Well, the accessor, to get the first component, we have the standard function first. And to set the first component, so given a pair of an old A, which we don't care about, and a B and a new A, we just put the new A into this slot. And we can, of course, do the same for the second component. That's traditionally called _2. So that's a lens from a pair of A and B's to B's. And the accessor is the getter is second. And then, of course, it's just symmetrical the other way around, like this. So we can do get first component of true Haskell, true, and we can set second component of true Haskell to Python, and we get this. So that's an example. And I'm not really sure I want to do this one. I think maybe not. I just show you on the slide. So it doesn't even have to be product types. I mean, in a sense, a pair and a record are still very similar. So a pair is basically just like a record with anonymous field names. So it's not surprising that you can do this for pairs as well. But you can also do it for things that have nothing to do with pairs or records. So here's an idea. We define a sign data type, which has 3 values, plus, 0, and minus. And then a lens from int to sign. So the getter is easy. So given an int, if it's positive, the sign is plus. If it's equal 0, the sign is 0. And if otherwise, the sign is negative. And now for the setter, right, so given an n, we want to like make it positive. So special cases, if it's 0, then we just arbitrarily pick 1. So we set it to 1, and otherwise we set it to the absolute value of n, which is then always positive. To set any integer. Yes.
Tony have a question, I think.
Okay.
Tony, go ahead.
Yes, can you hear me?
Yes, I can.
Okay, could you please just switch to the previous slide?
Yes.
Okay, no, actually the code, I can't, I did not quite understand why so we defined the data lens, and then now when we started defining the, like specific lenses like staff or,
Yes.
okay, looking at the type definition of lens, which has get and set, I just, I think I lost something. I've not really understood how it works or why it works. So we only have, you've defined get and set, but then when you are like kind of creating an instance of a lens, you initialize with some other types, but then I've not really understood why it actually works. You're
Okay.
passing a function to the maybe staff, but yeah, if you could explain a bit more.
Yes, sure. So the idea of a lens is it's just basically 2 things. It's a getter and a setter bundled up in one data type. So we use a record, field name get and set, but the values are both functions. So get is a function that, given a record, gives me the value of a specific field, and setter is a function that, given the record and a new value for the field, updates the record. So in order to define a lens, I mean, I must call the lens constructor with 2 functions. Maybe I could make it more explicit, at least in one example. So instead of writing it like this, I mean, I could write I could use record syntax to write it like this. So I was just lazy. I mean, I must define a getter and a setter.
Okay, yeah, that makes sense.
Okay. Thank you.
Thank you.
You're welcome. Right. So this is just like a somewhat silly example. So if I want to set an arbitrary int to something with sign 0, I set it to 0. And here, basically, if I want to set an arbitrary into negative sign, then I basically do the same as here, just with the other sign. So if it's 0, I set it to -1, and else to minus the absolute value. But that's not an important example. It's just supposed to show that you don't necessarily need something what we would call product type, so like a record or pairs or tuples. I mean, there are other examples of lenses, but the most common one are actually tuples and records. Right, this is just to demonstrate it. And there are laws how these lenses should behave, and I think they make like intuitive sense. And but some maybe don't and might still be useful, but I mean, it's similar to type classes, what we said. So I mean, we don't have to dwell on this for much, and I hope it just makes sense. So get set, you get back what you set. So if I first set to a new value a and then get, then I should get my a out. I mean, I set to a, then I should obviously get A. So I mean, if we try this here, I mean, for example, we set here we set the second component to Python. So if we now get the second component again, we expect to get Python out. So I mean, for this _2 lens, that seems to be the case. So first setting, then getting gets you back what you set it to. The second one is set get. Setting what you got does not change anything. So if I first look up the value of the field and then set to that old value, nothing should change. So in this example, if I first get the second component and then set the second component of true Haskell to this, then I get exactly the same back that I started with. And finally, setting twice is the same thing as setting once. So if I set to some A prime and then set to A, I could just as well have directly set to A. So I hope those three rules make intuitive sense, that they should hold. That's what we would expect of a getter and a setter. And actually, this example violates one of those three, but I forgot which one. But if you like, you can think about it. So this is not an example of a lawful lens. Right. And this is maybe a better example. So, but for me to get that to work, I need to change my imports. I must import the byte string package. Let me reload. So let me import qualified data.bytestring as BS and data.bytestring.lazy as qualified as LBS. And now I can write a lens from, can call it lazy, from strict byte strings to lazy byte strings. So as the getter, so given a strict byte string, it must give me the lazy byte string so that I can use LBS from strict. No, too lazy, I think. What's it called? I think it's called from strict. Yeah, from strict. Why? Oh, okay, sorry. It's in byte string, whatever. And the setter. So what do I need? I have a strict byte string and a new lazy byte string. And now to what? So I basically do BS to strict. Yeah. Why does that give me brief? Oh yeah, sorry. Right. So this looks a bit strange. Because I mean, our intuition is for a getter and a setter that this S, the S is bigger somehow than the A, that the A is just a part of the S. But in this example, I mean, the lazy byte string is not really a part of the strict byte string. It's just that you can basically convert a strict one to a lazy one without losing any information. And actually, we could do the same thing in the other way around. So we could also define a lens that we call strict from lazy byte strings to strict byte strings, where the getter is now too strict, and the setter is given by from strict. Oh yeah, okay. I must reload GHG. Right. But nevertheless, so this also fits into this framework conversion where we don't lose any information. And that's a specific, special type of lenses. It's a so-called ISO. And we will talk more about ISOs in the next part of the lecture. But they are like special cases of lenses where you don't lose any information. Normally, if you go from something big to one of its parts, you lose information. But you don't necessarily have to. So in this example, and there are other examples where you can like convert between two different types that contain the same information. That's a special case of lens, and it's called an ISO for isomorphism, which means same shape. Okay. And this one is also cool, but for that one, I have to import containers. Okay. And again, have to reload. So import data.map and import qualified data.map as map. Right. And this is traditionally called add. So given an A, and sorry, given a K, it gives me a lens from a map with keys K and values A to maybe A's. So the idea is that basically for each key, there's like maybe an A in the map. I mean, if the key is in the map, then there is actually an A. And if the key is not in the map, there is none. So that's like getting, what getting means. And what does setting mean? Well, to set to a just value means inserting into the map, and to set to a nothing means deleting from the map. So with this add lens, we basically in this one lens, we have three operations. We have looking up, inserting, and deleting. Let's try to implement this. So it's lens getter setter. Let me try to implement them separately. So the getter, given a map from key to A, must give me a maybe A. And we have this map.lookup. Oh yeah, and I don't need the case because map.lookup is exactly what I want. So I can just eta reduce this. And setter, so given a map and a maybe A, I want an updated map. And there are now these two cases. So given the map and nothing, or let's start with the other, it's just an A. I insert, add key K, the value A into the map. And nothing is I delete key K from M. Right, and I need ort on keys. And now I again have this trouble with that GHG doesn't know that this K is the same as that K. So I need to know what we always do when this happens. I need this extension scope type variables and have to write. Right. So this is actually nice. So let's do an example. So for example, I can do, I start with the, I can, for example, do add Kenya, sorry, set. So the lens is now at Kenya. I start with the empty map. Insert just Nairobi. So this inserts into the empty map. Key Kenya, value Nairobi. I can, for example, get at USA. Nothing. So USA is not in there. But I could, of course, set at USA. Just Washington. Okay, now I would get it out, and now I have both of them. And now I can also do set at Kenya, this thing, nothing. And I would delete the key Kenya again. So this at lens is actually very, quite nice, very useful. And it's also a lawful one. I mean, that's maybe not immediately obvious, but you can think about it that it fulfills these 3 laws that I wrote down. So it's actually a proper lawful lens. So that's another cool example for how you can use getter and setter. Right. Okay, and now we want to compose lenses. I mean, if you remember, before we had this lens idea here, I said that it's nice that you can compose them, and we showed you this example that, for example, I can compose city with address for the getter, for the accessor. But we said that for update, unfortunately, we can't. And the idea is now to, I mean, now that we have these first-class citizens with explicit getter and setter, that we can put this boilerplate that we earlier had to solve this example task, where we have like nested updates, to make that nicer. So let me go back. Right. So let's try this. Let's first call it compose. So we have a lens from, now I must just A to X, lens from S to A, and lens from S to X. So the idea is, for example, here you can think of address, the address lens. So S would be person, A would be address. And here you can think of the city lens. So A is address, X is string. And the idea is if I compose the lenses, I get a lens directly from person to string. So reaching 2 levels down. So let's see whether we can do this. So let's call this one AX and this one SA, and it will be a lens. So get. So get is easy because we know that getters already compose nicely. We saw that, sorry. We saw that before. So getters were anyway nice because they are just functions and they compose nicely. But now for the setters. So we have, what do we have? We have an S the big thing, and a new value for x. And what do we do? I mean, we want to change the s. So I mean, the only way to do this with what we have is using this lens here, the setter of that lens. So we use the setter of our SA lens. But to what value do we set it? So what is the new A value? Well, it's the old value, A value, where we change the X to this X. So we use the other setter, the AX, and set our to X. Is that right? No, I need, sorry, and what? So here we set the S, and here we must set, what do we set? The old A. So that's get SA S. Right. Is that right? Let me see. Yeah. Okay. So this is relatively complicated, but it's exactly what we basically did by hand here in this exercise. So to go 2 levels. So if I want to set the S, so I use the setter for the S, and now I must set it to the new value of A. What is the new value of A? Well, I use the setter to change the value of A. This is the old value of A, and I change the X in it to the given X. So it's exactly what you would do by hand with record update syntax. Right, and we can try it out. So we had this, what was it, the address lens and the city lens. So I can, for example, use get, compose city address, Lars, and I get Regensburg. But I can now also set compose city address last to a new city, for example, Nairobi. And it indeed reaches down into the address record, into the city field, and changes it to Nairobi. So now basically we have composability both for getting and for setting using this approach. So this is already nice. And using this, one could already write this go to easier. Maybe I should. Or maybe I should. Yeah, maybe. So now, I mean, I still have this mapf problem because, I mean, I can't handle lists. But now this one here, this F, I can now do much easier. So I don't need this anymore. So FP is now just, I use set, compose, exactly what I did before. So I compose city with address, and I set P to C. So I could try it. What was it? Nairobi and IOG. Right, and it works, I think. Okay, I mean, it's already much nicer than before, but I mean, we will do better. We will turn it into a one-liner. But yes, so this is already, the composability is already now not only for getting, but also for setting, because basically the complication, what makes it so complicated is now taken care of once and for all in this line here. And once we have this, we can compose arbitrary lenses together and use this. Let's see, okay, example. Right. Okay, now the next step is to not want to write this compose. And there's something from control category. Let me just import that. This, by the way, is only like temporary. We won't need that in the end, but it's useful to know anyway. So there's a type class, class category for arbitrary kinds blah, blah, and it has identity and composition. So, I mean, we know identity and composition for functions. So the identity function and composition to compose functions. And this control category class generalizes that. So functions will be an instance. So it will still work for functions. But the idea is now to make our lens a category so that we don't have to remember this compose word. We can use the old dot. The only problem is that the names clash. So it and dot is defined in prelude. So I need to hide those. Import prelude, hiding identity and dot. It doesn't matter to hide that, as I said, because functions are in particular an instance. So I still have identity. It's just more general now. If I now ask for the type of identity, it now is for an arbitrary category and not just for functions. Same for if I ask for the type of dot, it now, instead of just functions from B to C and from A to B, given a function from A to C, it also works for arbitrary categories. So then idea is we don't need this compose. Instead, we can make an instance category lens where. So we must think of identity. So we must have something of type lens AA for each A. Okay. Let's worry about that in a second. Let's first do the dot. So the dot giving a lens from A to X and the lens from S to A. We need a lens from S to X, and yoo-hoo, we already have this. I just copy the definition here. Then I don't need this anymore. And now I can just use this here in my example. Right. It remains the identity. So how do I define the identity lens? That basically zooms in on itself, not at a smaller part. So, but that is simple. So get is just identity and set. So given A and a new value for A, I just return the new value. Okay. Right. So now it's almost object oriented. So we have our dot now. The only problem is that it's the wrong way around. I mean, it's not really a problem, but I mean, in object-oriented programming, it would be address dot city, and here we now have city dot address. And actually, it would even work to remove the spaces, so the Haskell parser can handle that. I tend to not to, but some people, when they use lenses, they actually remove the spaces. So it really looks like in object-oriented programming. Right. So that's already relatively satisfactory, I think, by having this category instance. I mean, which basically just means we can compose lenses like this. It's already nice. I mean, we can already reach into a structure deeply and get something out, or also change it. I mean, set it to something new. So just another example. I mean, we have plenty of lenses now. For example, I could, do we have actually? Not that many yet, but I mean, for example, I could do, if I have a nested pair, I could do set. If I have first component of some second component, let's say, So I set second I have a nested pair. So I zoom into the second component, which is again a pair. And then I zoom into the first component, which is the Boolean. And I set it to true. So I have reached 2 levels in and done that. And of course, I mean, it can be arbitrarily many levels. So I could have, again, something here. Whatever. So I zoom into the second component, first component, second component, and change it. Okay. Are there any questions at this point?
Not so far.
Okay. Right. So next thing is, I mean, in this example, for example, I mean, okay, fine, I can set everything, but sometimes I don't want to set it. I want to apply a function to it. I mean, we saw examples of that. For example, in the state monad, we have this get and put to get our state and put the state, but we also have modify to modify the state. Same in when we talked about mutable references like IO refs. I mean, we also had this modify IO ref. So often, I mean, for example, what if I wanted to, instead of getting to here, if I want to, for example, increment the 45 by 1, which leads us to that we want something that we call over. So let me just check if we have a lens SA and a function from A to A. We want to get basically, I mean, I can write it like this. I can also write it like this. So I don't want to set the A that the lens focuses at to a new value. I want to apply a function to it. And of course, I could implement that now already. I mean, if I have a lens and a function and an S, what do I do? Well, I use the setter of the lens applied to my element. And what's the value I set it to? Well, I first use the getter of my lens and apply the function to what I get there. Right, and I can do this. So for example, in this example here, let me first use the setter again, but zoom in on the 45. So what's the 45? I lost track. So it's in the second component, the second of the second. So for example, I could set that to 0, but now I can use over. Now my lens, now my function, for example, the successor function. Sorry, and the signature must be here. So the successor function and or whatever would do times 3. Okay, so that works. But it's not particularly efficient because I mean, as we see here, I mean, I have to do this get. I have to reach all the way into my data structure to get the value out, and then basically to apply the set, I again have to reach all the way into my data function to get the value out. So even though it works, it wouldn't be very performant. So now the next idea is to change our lens definition. That instead of the setter, we use over here. Let me just check what okay, so over given A to A and an old value of S basically give me a new value of S, or like this. Right. Okay, so first of all, that looks as if all our code will break. So first I can remove this here. Now the first observation is that setting is a special case of, sorry, lost my way. Where am I? Here. So for example, now all this, in the examples, now the set is not defined anymore. But this is easy to fix. So here, because I can define set in terms of over. I just want to check whether it's still the same type. Yes. So given a lens now, a new lens with over instead of set, the old value and the new value. So the old signature we had for, I hate this so much. The old signature we had for set, I can now easily implement that. So setting a lens old value is just over what function over L what function S. And what's the function here? Well, I don't care about the old value of A I find there. I just set it to this new value, which I can also write as const A. Right. So a set is just a special case of over. I don't care about the old value I find. I just fix a new value. Okay. Now, of course, this was tedious enough to write all of this. I don't want to rewrite all the lens definitions. But it's okay because I can also define, as we saw in that what I unfortunately now deleted, we can also define over in terms of set. So given a getter and a setter as before, I can define a lens. So I can now define a lowercase lens function. So given a setter, S to A, and a getter, S to, a getter and a setter, so this is the setter, I can define a lens. So getter, setter, it's a lens. So the getter is the getter, obviously. But now I must define over. So given a function and an old value, and this is now, I probably shouldn't have deleted that because I already showed how to do this. So I use the setter to set my thing to the function applied to what the getter gives me. Right. So I can basically recover this. And now, because I reacted to this question and I made it more explicit. If I had done my old, we see the old definitions now. No, they also should all fail. Just a second. So I must remove this again to make it like more obscure again. So as I had it before. And instead of capital L, I must use my function L. Right. So I must do that everywhere. And here again, okay. And here as well. Okay. Why don't I get an error here? Okay, now what do I do with identity? So the getter is get and the setter is just, over is just, I could, of course, use this, what I have here as well. Or should. Why is, Okay, and now composition. So composition is actually much easier now. Because if we look at it, just a second here. So we have our two things. I mean, we have our AX. So over AX, what is the type of over AX? So given a function from X to X, it gives us a function from A to A. And what is the type of over SA? Given a function from A to A, gives us a function from S to S. So now we can simply compose those two. They are now composable. So over AX composed, I mean, normal function composition. Just make this clearer. Which is exactly what we need. So this becomes much simpler composition here. So over is just over AX function composition with over SA. Or at least it should be. Did I do wrong now? Then make a mistake. Oh, I did indeed make a mistake. It's the other way around. Sorry. But I mean, this is true what I wrote here. Just I got this wrong, the order, which is interesting that now the order is the other way around. Right. Okay. So now everything should compile again, I think. Right. And the examples here should work again. Okay. And also like our old set should work. Right. So yes, so that's one observation. So now basically by changing, I mean, we started with getter and setter, which is like the naive way you would, I mean, if I tell you you want to make like record field accessor, like first class citizen, I mean, you also know that, I mean, I did before I worked for IOG and did Haskell professionally. I worked for another company and did mostly C#. And I know in C#, I mean, it's an object-oriented language. There is this thing of getters and setters. So there are so-called properties, which are like generalized fields. And then you have getters and setters for those fields. And they can like contain logic, like validation or whatever. So that's like, I mean, an obvious point to start. But then we saw that we get composability, which is nice. That then we said we also want something like over. And then for performance reasons, basically it's better to not define over in terms of set, but to define set in terms of over, which we did here, and make over part of the definition. We don't lose anything because we still get our set function. It's just not no longer type of the, I mean, a field in the lens type itself, but nevertheless, we still have set once we have a lens. And we still have our composability. And it's even much nicer now. So now this looks really beautiful already. Okay, so that's the first step. And maybe now it's time, let me just check. So very nice. Right, so before we go on, maybe are there any questions? Otherwise, I would suggest we have another break.
Not yet, but yeah, we're on time to take another break.
Yes, I think so. I'm not sure I will get done with this lecture today, but I think I should take my time, and we have plenty of time, right? Because this is quite complicated anyway. But I think it's a beautiful topic, so it would be a pity if we rush through it.
Yeah.
So yeah,
Worst
let's
case
just
scenario, we just add another day to the to the schedule.
yeah, exactly. I mean, we wanted to like slow down a bit anyway, so I think it's
Mhm.
fine.
Yep.
Oh, I just see. What's that? I'm just confused why we have. Oh yeah, sorry. Oh, in the slides I keep this compose around, so I didn't inline it. But this is sort of nice. Is that just? Let me just. That is one thing I still want to do. Oh, okay. I see. In the slides I did differently. I mean, here I used my lens constructor. This no, I didn't. I used my lens function with getter and setter. So on the slides I used the constructor, and so then the getter is the identity, but what is over? So given a function and an old value, well, I just apply the function to the value. And of course, so over is just, sorry, is that correct? No, sorry. Yeah, I think it is. Given a function and an old value, just apply the function to the value. Right. And this is just function application. So I could also write dollar for this. And then like so, that's where the slides come from. Okay, so I did the slide different there, but I mean it's anyway correct. Right. So basically the plan. So we can have a break now, and then the plan is to do a couple of more steps. So we are quite far already. So now we have like arrived at this definition, and now the next idea is to do a couple of more steps until we end up with basically where we don't even need the get anymore. And then everything, we don't even need the category anymore, and everything is beautiful and cool. But let's see. Okay, so maybe 5 past 5.
Okay. Yep. 10 minutes.
Okay. See you then. Okay, should we continue? Are there any questions?
No questions.
All right. So now, next step, we want to have something like over IO. Right. So now the idea is, I mean, that's all very good. So we now have, we can get, we can set, and we have over to modify the A inside the S. What if we want to use an effectful update? So for example, in IO, instead of something from A to A, we have something from A to IOA. Then of course we can't expect to get an S again. I mean, what we can hope for is to get an IOS again. And I mean, that would be nice to have. So one way to do this would be to make our lens type more complicated and add this over IO as well. However, we don't need to because we already can implement over IO with what we have so far with just get and set. So let's do this. So over IO. So given a lens from A to B, and now, sorry, from S to A, it's always this traditional name. Now something from A to IOA. We can already define something like this. So given the lens and our function, so what do we do? I mean, first we can use the getter of our lens. We also have an S. So first we can use the lens of our the getter of our lens applied to our S to get an A. Then we can apply F to it. So now we have something of type IOA. How do we get iOS? Well, we know how to go from an A to an iOS, or rather from A to S, namely using the setter. And now we remember that IO is actually a functor, so we can fmap. So the idea is now to fmap something over this. And that something must just be from type A to S. So given a new A, give me the new S. And that we know. So given a new A, how do I get a new S? Well, with our setter, set L S A prime. So I can eta reduce here. Right. So the trick is to use that IO as a functor. So I know, given a new A, how to, I mean, with fixed S, given a new A, I know how to get the new S, the updated S, and I just fmap this to go from a new IOA basically to a new iOS. So we can try this out. Let's say, I mean, we need a function from A to IOA. Just an example function, for example, for strings, foo string to IO string, foo s, note how I cleverly use, instead of concatenate, I now use the monoid, the diamond operator. And nine. And now I can do stuff like over IO, our name lens, the foo function applied to Lars. Now it says old name Lars, and I say, I don't know, Dr. Lars. And now it gives me in IO this updated person where the name has been changed to this. So effectful updates. And the next step is we realize that nothing in this definition here did we use IO. I mean, all we needed was that IO is a functor. So of course, because we do Haskell, we immediately generalize. So if we have an arbitrary functor, the very same definition still works. And all I have to do is now, instead of over IO, use over F here. And the same stuff still works. Whatever. Right. So that's over F. Now let's see. I don't want to get out of sync. And yes, and just look as an observation. If you recall the type of traverse, if you squint a bit, so I mean, here we have this lens thing, and then A to FA, S to FS, and in our traverse we had A to FB, something, yeah, TA to F of TB. So it's, I mean, not the same, obviously, but it looks like enticingly similar. So we'll come back to that observation soon. Right. Okay. Okay, we did try it. So now, next step is we, in our lens definition, we instead ask for this over F. Let me just for 1 second comment everything because I don't want so many errors. So functor F, A to FA, S to FS. Okay, now I get a type error because, so I think I have to write for all F. Right, and now I get an error that, yeah, this is called rank n type or polymorphic, what's it called? Yeah, it's called a rank n type. So, I mean, all our for alls until now have always been like at the, I mean, at the top of a type. So in front of everything else, not somewhere in the middle. So in standard Haskell, this wouldn't be possible, this definition. But of course, like for everything, there is an extension in GHC called rank n types. And now this is fine. Okay. So now, of course, I mean, what do we do about, I mean, we don't want to change everything, right? So first question is, if we have this over F, can we recover our old over? And of course we can. So our old over had the signature, we have a lens, the function from A to A, and we want a function from S to S. And now if you remember the beginning of today's lecture, we had this similar situation where we had map M or map A, and we wanted to recover map. And there the trick was, I mean, now we are in a similar situation where we have this F that we can play with. So we can instantiate F to a functor that suits our needs. And the same trick that worked beginning of this lecture using identity works here as well. So we just, so given a lens and a function and an S, we just use our over F of the lens applied now to the function identity composed with F. I probably have to import something. Apply to S, and then we have to run identity. And I can either reduce the S, and I need to import identity from somewhere. There's something called control monad identity, for example, or the data functor identity. Let's do this one. It's in the base libraries. Okay, and now this compiled. Yeah.
Oh, sorry.
Yes.
I think it might be just me, but I lost you for a couple of seconds.
Okay.
Yes, but
Uh,
all good.
uh, Okay. Right. So it's the same trick we used like beginning of this lecture to get from map A to map by just using the identity. I mean, back then we needed that identity was applicative. Now I only need that identity as a functor. So it's the same trick. I mean, I need an effectful function. So I have one from A to A. I just compose it with the identity constructor to get something from A to identity A. Then I can use my over F. And then in the end, I end up with something of type identity S. So I have to unwrap the identity new type constructor again to get that back. So this is cool. And I think now everything else should work again. Of course, I don't need this over F anymore. This is now part of the lens definition. Right, and here I just have to see whether this still composes so nicely. I hope it does. Yeah, so that still composes just as nicely as over. 74. Okay. Okay, and here now, of course, I shouldn't have deleted this. I mean, it's the same trick that I have to fmap. I mean, the definition of over F, I shouldn't have deleted that one. So so what is it? We have a new A, and we want to set this to A. So it's just a setter. That was the definition that I like to quickly delete it. I should have put it there. Right. And I think on the slides, I write this more compact by using this operator for fmap. But then I need to parenthesize differently, like so. Okay, so now we have replaced this over F with, the over with over F. We can define over in terms of over F by using the identity functor. We can, I mean, as before, define set in terms of over, that hasn't changed. And we still can recover a lens from a simple getter and a simple setter. So we saw this definition before when I just defined over F. So again, we haven't lost anything, but now we have this over F automatically. But I mean, of course, at the moment, I mean, I could have defined that as I did before. So it's not clear what this gives us. But now the cool observation is that I can define get in terms of over F. And again, if you remember earlier today, with this map A, I defined map in terms of it using the identity functor. And I defined fold map of it using the const applicative. And similarly, now we can do get. So get, given I mean, this is of course silly. Let's call it get prime. Let me just check whether on the slides I also do it like this. Right, yes, I do. So get prime. So given the lens, I can just look up the value of S of A. So let's see. And of course, I mean, I could just write this, but I now want to show that I don't need the getter. I can just do it with over F. So let's see. So given a lens and an S, what can I do? And the idea here is to use the const functor. And so basically do the same what I did here, but now with, I think it's called get const over F const. And it complains because const is not in scope. Data functor const. And there's no f. I think it's just const. Right. Right. I mean, this looks a bit strange, but the point is, I mean, what does const do? So what's this over f in this case? So if I just have const, and this is now const a. So this is, maybe I should say, using over f at f equals const a. So this function here, sorry, the over f function, this one. So the functor is now const a. So what I need here is something of type a to const a. This is just const. So it just wraps the a it finds inside the s in this const new type wrapper. And now the cool thing is that, I mean, on const, the functor instance completely ignores the function and just keeps the constant value as is, as we saw earlier today. So this this f map, basically in the over f, doesn't do anything, and I still have my. So now I'm at type. So now I'm at type const as, but the const as is still just an a. So the s is completely ignored in this const functor. That is the trick. And then I unwrap my a with get const. So we can try this out. So I can do, for example, get prime name class, and I do get my name. And why would I want this? Well, the cool thing is that now I can get rid of this. So I only need the over f. And of course, now I can just call it get. And I don't need this here anymore. Sorry, just the comma. And let's see. Okay, I don't need it here anymore. Okay. And now, I mean, first, of course, because now it's only one field, I could use a new type. But I don't even need to. I can just remove this completely and just, sorry, oh, what did I do now? I can just use a type synonym. So I forget about this, and I forget about this over f name, and just do this. And now I must just change very few. So this is basically, lens is just the over f. So I don't even need the name over f anymore. So now I just need to change very few things. I mean, I don't need this constructor anymore. And I can write this. I mean, the lambda is now unnecessarily complicated, so I can just write it like this. Okay, and here, so this goes away, this goes away, the over f goes away. And I can't even write an instance anymore because type synonyms, we can't have instances for that. But I don't need to because it's just function composition now. So I just, I don't even need this anymore. Because we know the over f's. Maybe I should just show you that the only interesting thing is it's like the other way around. So to compose a lens from ax with SA, I basically compose the functions in the other way. So now I can get rid of this. I don't need it anymore. I don't need this anymore. I don't need the category stuff anymore. It's just function composition now, because the lens is now with this newest version. Where is it? Here. It's just a function, a plain old function. And if I have another lens, just to demonstrate, so Let me just copy this. If I now have a lens AX, X, X, A, then we see that if I write it the other way around and like this. See, so we can just compose it. This is a function from here to here. That is a function from here to here. So I can just first do this function and then do that function. So composition of lenses in this form is just given by function composition. So I don't need the over F anymore. The lens is a function now. Just checking. Okay, the only thing that changes is that now it's the other way around. This now magically all works. Right, so and right, so this is now our definition that we arrive at. And I mean, basically the whole lecture to this point, I mean, first I wanted to motivate why one would want something like lenses, because the motivating example is that record syntax is like awkward if you have deeply nested data structures. And of course, I could have just thrown this definition at you, but I wanted to motivate how one arrives at, because I mean, this is like a complicated signature. I mean, it's a rank n type. And it's, I mean, it's not at all obvious why this type has anything to do with getters and setters. But I hope that I like motivated this by going step by step from the naive definition, just using a getter and a setter, like step by step to arrive at this one. And I mean, and these are called van Laarhoven lenses, so this form. And that's not the only way. So there are other, I mean, there are a couple of lens libraries on Hackage. The most prominent and widely used one is called Lens and uses this definition more or less. But there are alternatives, and there are also actually advantages to basically sticking with more or less this getter-setter approach. But nevertheless, I think this is a beautiful like abstraction, or I mean, it's very hard when you first see it to understand what this has to do with accessors and getters and setters. But I mean, it's very cool. I mean, the idea is that it's just a function. The lens is just a function. And therefore you get composability, I mean, just for free, because you have just functions. And all, I mean, the magic somehow is that with this one definition, you get all these things over, set, get, and our over F, over IO, and so it's all just automatically works. So I mean, to do our example with over F here, now I don't need the over F anymore. I mean, the lens just does this. So I mean, this still works, and all the other examples should also still work. So right. So by having this weird, complicated signature, but just a function, we get all these things that one would associate with like accessors, modifying field in a record, setting a field in a record, getting a field in a record, and of course all our example lenses. And we can still construct this thing, this complicated function, just with a getter and a setter. So in principle, one doesn't even need to like know this. I mean, you can in principle just construct lenses using getter and a setter as before, and then you have all the nice functions so coming with them. Right. And what I said earlier is still true. So there are like template Haskell and ways to automatically get rid of this boilerplate, so you don't have to write things like that yourself. So all our examples still work. And I mean, this also still works, except it's the other way around now, but now it's even more than in object-oriented programming. So, I mean, this is now how it would be there. So person.address.city. So are there any questions at this point?
No, but there's happy people saying that it's magical.
Yes, I also think it's magical. And right. I did show that how you can get this, I hope. Yeah. Okay, I got rid of category. Right. And now the last chapter for today, I hope I can still do this. So lenses, as we have seen now, allow us to zoom in on one part of a structure. So the name of a person or the city of an address. And they are naturally composable because they are just functions. And now what we also would like is given a structure with many parts of the same type, like a list, like in our example, the list of persons, the staff, we would like to zoom into them simultaneously so that we can do the same thing to all of them at the same time. And we want to be, and something like that, we will call it traversal, but we want to be able to freely compose traversals with lenses and each other. So we want a similar shape. So we want to define a type traversal similar to this one with a similar shape here so that we can freely combine lenses and traversals. So that's the idea. And the method traverse of class traversable has a very promising signature. I mean, I mentioned that before. So this leads to our definition of traversal. So if we, maybe I can just, yeah, whatever, I can, I don't know, let me write the definition of traversal underneath. And let me just, so our definition of traversal will be very similar, except for functor, we demand applicative. And remember, applicative appeared when we talked about the traversable class earlier and traverse. And this will be exactly the same. Right. And because of our definition of this definition, and if we compare again with the type of traverse that we saw earlier today, we see this does have exactly this shape, provided that we look at the special case where A equals B, so this is right, and S equals TA, which leads us to our first traversal, which we call each. It's for, if we have a traversable container T, it gives us a traversal from a container of A's to the contained A's. And the definition is just traverse. Right. And now because of this shape, we see that we can, because it's just functions that look the same. I mean, only these constraints are different. We see that we can compose everything. We can, I mean, we already saw we can compose lenses with lenses. We saw earlier today that we can compose traversals with traversals. I mean, we saw that with this example of traverse. And we see also that we can compose lenses with traversals and traversals with lenses, but because now we have two constraints then, functor f and applicative f, and applicative is stronger than functor. So we see if we compose a lens with a traversal or a traversal with a lens, we get a traversal, which also makes sense. I mean, because if, I mean, lens allows you to zoom in on one element of a structure, whereas a traversal many. So if you first like have many and then zoom in each of those into like one, you still in total zoom in on many. So we can freely, I mean, we basically have this matrix that, I mean, I don't know whether I should. So if we have like a lens and a traversal, and we compose, no, I can't do this. Can't do that. So if we compose a lens with a lens, we get a lens, and everything else, we get a traversal. Right. Now, let me just try to keep somewhat in sync with what I did here. Right. So now, of course, we have these niceties here, over, set, get, and so on. And we would like to have something similar for traversals. And this is actually easy because here, for example, I mean, we have this lens, and lens is now just a type synonym for this. So we could just replace this. Sorry. Or maybe, sorry. Don't know how to do this. So let me just like type it in. So functor f. Just check how I did it here. Right. So we have this. So I just basically plugged in the definition of lens. So I haven't changed anything yet. And like this, I wouldn't be able to use over with a traversal because a traversal only guarantees me that I can do something for every applicative, but in all lens guarantees that I can do something for all functors. So I can't, I mean, where the lens is expected, I can't use a traversal because this is a weaker condition functor. However, I don't need this in order to define over. I don't need this for all functors. I only need it for the identity functor. So I can get rid of all of this and just replace the F with identity, and this still compiles. And now identity, as we saw right at the beginning of this lecture, is actually a monad, so in particular applicative. So that means it works for traversals. So let me just reload. So I mean, we had, for example, over and our whatever the successor lens, or yeah, let's use a different example. Let's use logical not. Sorry, let's say the first component element in a pair component lens. Let's use the function not and have a pair true Haskell. So that applies this function to the first component. So now, because I changed the definition, so now it also works for traversals. So instead of this, I can use the each traversal. I mean, it's the only traversal we know for now. And now, for example, use a list of Booleans. And that works. It just works. So it applies the over function to all elements of this list. I mean, which is our old map, of course. I mean, over each is basically fmap. But nevertheless, it's cool. And I can compose. So if I have, for example, a list of Booleans and strings, Haskell, false, Python, false, Java. So now I can use composability. So so first I use the each traversal to zoom into each element of this list. And then I use my _1 lens to in each element zoom into the first component. And it just works. And I could have For example, if this list is the second component of a pair where the first is an int, it just works. So that's that. Now we want to do the same for, or similar for set. So what did I need here? I mean, here I didn't use anything. So that's also identity, I think. Let me see. Right. I mean, I wrote over in, I mean, I wrote set in terms of over, but over is in terms of identity. So I can change this to use over F instead, which is just L. Let me do this first. Now, so I must do identity. Now run identity. Sorry, got it a bit wrong, I think. Oh, no, sorry. No, sorry. I can leave this as is. I mean, what did I do here now? Right. Basically the same trick. I mean, right. Sorry, I was confused for a second. So the same trick. I mean, I use in the definition of set, I use over. But for over, I don't need the full power of lens. I just need it for identity. So I can do exactly the same thing that I did there. Sorry, I was confused. So just plugging in the definition. Right, and that also compiles. So that means my setter also works automatically for traversals. So let's see. I had this one. So instead I can use set each false. And I set everything to false, or set each Haskell to, I mean, if I consider it as a list of strings, X. And maybe to have, I mean, that I don't only have lists, let's again quickly repeat this tree type, tree A, leaf A, node, tree A, deriving show, functor, foldable, traversable. So I need this derived traversable extension. Right, so now, because each works for all traversable containers, it would also work for trees. If I have our example tree again, tree string, what was it? I mean, it doesn't matter, but node, leaf Haskell, node, leaf Python, leaf Java. So I have our tree, and now I can also do set each tree C. Right. And I mean, of course I can, I mean, this is now, I mean, I have the each traversal, and I can do the same I did earlier. So I can now do whatever, set each tree X. So now each character in the original tree will be set to an X. And of course I could do over and these things. Right. So cool. What about get? For get, we use, I mean, first of all, get is actually historically called view. So let me just rename that. I don't know whether I used it anywhere else, probably not. So it's called view. And now let's do the same trick. So, I mean, as in over and set, we only use the identity functor. Now for view, we only used the const functor. So I can do the same trick, replacing length with a to const a. The const functor, const a functor. So const a. S to const as. Right. And that still compiles. But remember that const is not unconditionally applicative, only if A is actually a monoid. So if we try something like view each true, false, we are out of luck, because now our type A is bool, and I mean, const bool is only, I mean, would be a monoid if, or an applicative, we need applicative, would be an applicative if bool was a monoid, but bool is not a monoid. However, if we have a monoid here, it would work. So if we do, and what, I mean, one example of a monoid is strings. So if we have Haskell is beautiful, then actually view works on this as well, on the traversal. And it uses the monoid instance to basically slam it together. But maybe we want something else. I mean, we want to like view all the zoomed in elements as a list. And I think, let's see. Ah, yeah, here's another example. Okay, fine. Another example of a traversal. It's maybe not a bad idea, because until now we have only seen the each. So there's also the both traversal, which is a traversal traversing. If you have a pair where both element types, the first and the second component, are the same, we have a traversal that visits both of them. So let's see. So we must implement this. So given, sorry, where are we? Here. So we have a function from A to F for some applicative F, FA. So we have this function, and we have an S, which is now of this both type. So we have a function and two A's. So what must we do? Great. Oh yeah, sorry. I mean, they're of the same type, but of course, I can't call both of them A. Okay, so I need something of type F and FA, A. And I don't know anything about F except that it's applicative. And I need a pair of A's again, but in the applicative F. So the only thing I can do, the logical thing, is to do this. Right. Yes, I should have done this before. So now I have a different example for traversal that doesn't come just from traverse. Because this is not, I mean, I can't use each here. Because there's no traversable container anywhere. So I can now do whatever, over both to upper A, B, import data character to upper. Right. And of course I can freely mix them. So I could do each, both. I have a list of such things. Right. So that's another example of a traversal. Traversal, both. Okay, view. So that works for lenses, but they have this monoid problem. Okay, and we can do this to list of. I just wanted to check the name. So basically this only works if A is a monoid for traversals, but the idea is to just, instead of wanting an A as a result, ask for a list of A's instead. So this is now applicative because list is a monoid. So const list of A's is applicative. And now, of course, I can't just do const. Instead, I must first convert it into a list. Sorry. Yeah. You just not be cute here. Why doesn't it work now? Oh yeah, I want a list of A's in the end. So it was okay what I did earlier. Don't need this. Keep that. Okay. So pure in this case, I mean, we are now in the list, so that just pure for lists. I can show you pure X is just, or pure true list of pool. It's just a singleton list. So I first wrap it in a singleton list and then I do this const trick I did before. And now, because const list of A is applicative for any A, now this, I mean, the view didn't work. So let's just view each, that didn't work. But if I now use to list of, then that works. I mean, in this case, it's boring because it just gives me the old list back. But I mean, I can do the same for our example tree, for example. And now I get the values of the leaves as a list. And of course, I can again combine that with other things. So each. So now I traverse the leaves of the tree and then the letters of the strings and wrap them all up in a list. So I get this. Okay. Let's see whether there's much left. Just a second. No, there's not much left because now we are, I mean, for today, so we are almost through. I already told you about composition. Showed you examples. Said that. Okay, and now we are basically at our example here. Now we can, oh, where was the second version? So now I don't need to do anything awkward here with the stuff anymore. Sorry, the foo was, I copied too much. So now I can just use set. My lens is just, so first I zoom into the staff, which is a lens. Then I go over each element of the staff, the persons, zoom into the address, zoom into the city, do this for the company, and set everything to C. And go to double prime, Nairobi, IOG. Ta-da. So now we have, and if I now want to have like object-oriented flare, then I can do it like this as well. Right. So yeah, lenses and traversals are, and we also saw, right. So I mean, those are two very important flavors of lenses. And as you can see, one can already do amazing things with that. So it's a lot of fun, I think. And in the next lecture, we are going to look at two more types of traversal, of lens, of optics. They're so-called prisms and they're so-called ISOs. So you saw ISO already in action with this lazy. So there's a special class of optics for that. And then there's something called prisms. So prisms are for things that might not be there. So for example, if you have either, then there is a right prism. So if the either happens to be a right, it will zoom into that value, but if it's a left, then it won't. So those are called prisms. And that's then, I mean, they are like, I mean, at the end of next lecture, I can show you the lens library, but actually I can show it to you now because it's always like funny. So lens package. It's like one of the most infamous libraries in Hackage. And here's like this big chart of stuff. I mean, there's also something fold, setters, getters, whatever. And yeah, there are lots of things that one can do. But we will restrict ourselves to those, is it 4? Yes. Lenses, traversals, prisms, and ISOs. But I think lenses and traversals are the most important ones of those 4, and where you also get the most bang for your buck. Right. So using these things, it's easy to reach deeply into some nested data structures and manipulate them or get information out or set things, as we saw. Okay, I think I should stop here. I mean, time is up, almost perfect timing anyway. But if there are questions, of course, I'm happy to answer them.
Not yet, but maybe we can wait a couple of seconds.
Of course, yes, happy to. Try to think, is there another nice example? One can do. Oh yeah, and one last thing is that we will do, I think, in the next lecture. So right now we had this lens type, which is actually in the literature, it would be lens prime. And the actual lens type has 4 type parameters. So the idea is that not only can you, that you can change the value of A. So, right. But this is a small change, so it won't require much code change. But that's then the full beauty of lenses. You can also change the type of the element sometimes.
Okay, so I think we're good. Okay. Big topic. I'll need a rewatch and probably raise questions via Discord. Okay, no problem with that.
No, of course not. Ask as many questions as you like. And we can also, at the beginning of next lecture, you can ask, of course.
Yep.
I think it's a very cool, I mean, it's really beautiful, I think. And amazing that it's possible to do things like that in Haskell. And I mean, it doesn't have any built-in support for that. It just, I mean, falls out of the power of Haskell automatically. And it's also relatively new. I mean, it's, I don't know, 10 years old or so. So it's a relatively modern discovery that you can do these lenses. And actually, it's practically it's actually used. I'm not sure about like Cardano itself, maybe not. But although some libraries in Cardano use it, Plutus related, like the testing stuff, this model-based testing for Plutus that used lenses a lot. So in particular, I mean, for example, just one minute. There's something called chart Haskell. No, it's called charts, but I think it's on Hackage. That allows you to do beautiful diagrams in Haskell. I just want to show you just quickly. There's somewhere. Is it there? Not sure. This stupid thing is in the way.
You can move it. You can click and move
Yeah, I moved it just.
Okay.
I mean, there's a gallery. I mean, you can do like charts like this. And there are like millions of settings. I mean, not really, but thousands of settings, as you can imagine. And I don't know, I just arbitrarily click on something here. And you see there are these underscores in the, I mean, there are all these, settings and then you can say, I mean, the title and the style and the style, I think is a record. So it's records and records and records. And so it would be like very difficult to actually work with this and set your settings. And therefore they use lenses. So then you can basically, I mean, you have like a default setting, and then you can just say whatever dot x-axis dot style dot color dot whatever equals black or so. So I mean, especially for something like this, where you have like, I mean, hundreds of settings that are in deeply nested record types, it's very convenient to use lenses to work with them and set settings. So it's like very practical actually. So people are actually, I mean, it's not just like theoretical fun or academic fun. It's actually used in practice for like real world applications like charting. And so, yeah, it's useful. Okay, then if there are no other questions, then we can stop for today. So I wish you a nice rest of the week and a nice weekend. And then I'll see you or hear you on Monday. Thank you very much.
See you, everyone.
Thank you. Bye.
Thank you. Bye.